The second derivative is very useful for talking about the concavity of a curve, the shape of it. The first derivative measured the change in the y value, which we called the slope. But remember, a derivative measures change. So the second derivative measures the change in the first derivative, or the change in the slope. And that's what's called concavity. So concavity is the change in the slope. Now we say when that concavity is greater than 0, well, what does that mean? The second derivative is greater than 0. We're saying the change in the slope is a positive number. Let's just have a look over here at the parabola and see what that means. If I start from the left-hand side, the slope of the tangent here would be negative something. That's reasonably steep. But as we move from left to right, the tangent's still negative, but it's getting shallower and shallower and shallower and shallower. So the change is positive. It's becoming a bigger and bigger amount. Then we get to 0. Then we start getting positive. But it starts with a shallow amount, so a small amount, gets bigger and bigger and bigger and bigger. So it has a positive change. It's moving from a negative slope to a positive slope. All we really need to know then, we don't need to know the number. We just need to know whether it's positive or negative. So if we know it's positive, we've got a concave up curve. The curve is that shape. And if it's negative, the reverse must be happening. No, it's concave down. What happens in between? In between is a possible, it might not be a point of inflection, but it's a possible point of inflection, and we'll talk a bit more about that in a little while. Let's more focus on the concavity. This time I'm going to draw a sketch of a curve. I'm not even going to use the first derivative, only using the second derivative. And again, it's just a sketch. It won't be incredibly accurate, but it'll give me an idea of what the shape of the curve looks like. So if I'm only using the second derivative, and we're talking about a polynomial here, we know the basic shape of a polynomial. What I'm really interested in is where does it change from having a positive concavity to a negative concavity? In other words, let's investigate, find when it's 0. That has got to be the point where the concavity changes. Let's find the second derivative. There's my first derivative, 3x squared plus 10x plus 3. Second derivative, 6x plus 10. So I'm interested in when is that going to be, well, I'm saying greater than 0. I could have investigated less than 0. I could have investigated equal to 0. 0 is the key point I'm looking for here. So I'm investigating when is it concave up. It's the second derivative is greater than 0. I want to know when 6x plus 10 is greater than 0. So it must be when it's greater than minus 5 on 3. All right, let's draw a quick sketch. Minus 5 on 3 is the key point. Again, it's a rough sketch. The y value, I'm not really interested in, other than, again, whether it's positive or negative at this stage, just to get an idea. It turns out to be a positive number, so I'll just plot it somewhere up there. But the curve must look something like that. Minus 5 on 3, I'm saying that is where it's going to change to going concave up, and before that it was concave down. There's the basic shape of the curve. So it's a very rough sketch, but I've got an idea of what this picture looks like. Again, I don't really know, with the information I've used, whether that minimum turning point, is it to the right of the y-axis or the left of the y-axis? Well, I could use the first derivative to locate that, but again, it's just a rough sketch. I'm just trying to get the shape of the curve here. All right, let's talk about those turning points in a little bit more detail then. If I combine those two ideas about the first derivative and the second derivative, because we know every one of these turning points are stationary points. It has to have a horizontal tangent in order for the curve to turn. So to find our turning points, the first thing I would do is find stationary points and then classify them. Is it concave up or is it concave down? So if it is concave up, I must have a minimum turning point. Concave up, I'm down the bottom, got to be a minimum turning point. If it's concave down, I must have had a maximum turning point. So again, if I combine the two pieces of information, it's a stationary point, it's concave up or concave down, it tells me exactly what type of turning point I have. Now let's look at this cubic. X cubed plus x squared minus x plus 1. In order to investigate it, I'm going to need those tools. So that's the first thing we do. First derivative. Second derivative. Okay, I have my tools. Again, explain what you're doing in your solution. The first thing I'm doing is I'm going to locate these stationary points. So I know stationary points occur when the first derivative equals 0. This is what I'm attempting to solve. Let's solve it. We have a quadratic to solve, but that's all right. We can solve quadratics fairly easy. Hopefully it factorizes. If not, we've got a quadratic formula we can use, whichever method we choose. But we end up with 2 stationary points. Now, yesterday we just used the first derivative and we drew a table of values. A little bit time consuming. The second derivative gives us a quicker way of doing it, because now it's just a substitution. So I'm looking at when x equals -1. If I substitute that into the second derivative, I get a negative number. Remember, the actual value of the number is irrelevant. I'm interested in whether it's positive or negative, so I make that statement. Yeah, I got an answer of -4, but what I'm interested in, that's less than 0. That's the interesting piece of information that I want to highlight, because that's telling me the curve is concave down. It's a stationary point, it's concave down, therefore it's a maximum turning point. A little bit quicker than drawing the table of values. Let's investigate the other one. So when it's a third, we substitute in. By coincidence, the actual number for is the same. Happens a lot because of symmetry of curves, but it's not always going to be. Just one's positive, one's negative. But this is a positive number. That one would be a minimum turning point. And we've got that same sort of information we saw yesterday, but without drawing the table of values. Now, that's not to say that drawing table of values is still not a useful idea. Because if you've got a function that's quite complicated to differentiate, then possibly it's going to be quicker to use the table of values than go and differentiate a second time. So it really just depends on the function you're investigating, which technique you would use. Okay, let's talk about these things, these inflection points. What happens when it doesn't have concavity, when it's equal to 0? What's the story there? The inflection point is that. It's when there is a change in concavity. That's the point when it goes from concave up to concave down, or vice versa. How do we see if there's a change? Well, we check either side of the point, similar to what we did yesterday with the first derivative. So let's look at this cubic. All cubics have an inflection point. So I know it's going to. In fact, any polynomial of odd order must have an inflection point. First derivative. Second derivative. Find the inflection points. In this case, I'm not interested in the stationary points, inflection points. So I write down what I do. Now that very first word is extremely important, because unlike when we're finding stationary points, when we solve the first derivative equals 0, we will definitely get a stationary point. It'll be a stationary point every single time. The same is not true with the second derivative. And that's why we say possible points of inflection. And they might not turn out to be points of inflection. They are possibilities. That's when the second derivative is equal to 0. So the first thing we do is to locate the possibilities. Now in R1, we just have one possibility, -1/2. We now need to confirm whether it is or it isn't a point of inflection. Now, because it is a cubic, here's the interesting thing. All cubics must have a point of inflection, so this must be a point of inflection. Right. But that's not good enough for a proof. We need to test. So let's draw up a table of values like we did yesterday, but this time it's the second derivative I'm testing, not the first derivative. That's what I want to check either side of the point. So I know that at -1/2, that's the point I'm testing. That's where the second derivative is equal to 0. I've drawn a horizontal line because, well, how do you describe no concavity? What shape do you draw? So I just draw a horizontal line there. But I need to pick a point on the left-hand side and the right-hand side. Again, I can't go past any other possibility. In this case, not an issue because there are no other possibilities. On the left-hand side, I pick -1. Substitute it in, -12, concave down. Okay, I know this one's concave down on the left-hand side. On the right-hand side, I'm going to test the point 0, very easy number to substitute in. I get +12, concave up. Again, in your solution, make sure you put this step in. You make the point that yes, there is a change in concavity. That is the key bit of information that you're looking for here. So you need to identify, yes, I've confirmed this. There is a change in concavity. Well, if there's a change in concavity, it must be an inflection point. So basically you're explaining why you can make that statement. Why can I make that statement it's an inflection point? Well, because I've just found out there is a change in concavity. Remember I talked about this very special point, the horizontal point of inflection. It's an inflection point that is also a stationary point. So what you'll find is the first derivative will equal 0 because it is a stationary point. The second derivative will equal 0 because it's an inflection point. But here's the good one. The third derivative will not equal 0. Third derivative? There is an alternative way of finding inflection points. But if you think through the process logically, it makes sense. Because remember what the second derivative is. It's the point where there's a change in concavity. What tool measures change? The derivative. So if we differentiate the second derivative, we have a tool that will test for the change in the second derivative. So the third derivative will test to see whether there's a change in the second derivative. So back to our question. So an alternative way, yes, we were going to find our possibilities. The second derivative is equal to 0. But here is the actual rule. Okay? It's more than just the third derivative. If the first time you substitute into the derivative and you get a number that is not 0, an answer that is not 0, and if that is an odd derivative, so third derivative, fifth derivative, seventh derivative, and so on, then it's a point of inflection. Okay? It will be a point of inflection. If the first time you substitute a number in and you get an answer that's not 0, and it's an even derivative, then that one's not a point of inflection. Right? So the fourth derivative, the sixth derivative, the eighth derivative, and so on. Now the functions we look at, usually the third derivative is good enough, it'll go there. But theoretically you could keep going. So for our one, here's what we would then do. We've located our possibilities. But you see, back when I was working out the tools, I would have found the third derivative as well. And the third derivative for our one is a constant number 24. So I would have done my solution exactly the same and said, well, possible points of inflection. So would have found the possibility at -half. Well, I'd substitute into the third derivative. The third derivative is a constant 24. Hang on a sec. 24 does not equal 0. That means that change in concavity exists. Because if you think about it, it could be any number. If there's a value, it's saying there is some change. That's why if it's not equal to 0, it must be a change. The only time it won't be is if it's 0. It's not equal to 0, therefore there is a change. Again, make sure you write that down, especially for this method. As I say, there's a lot of teachers who go, hey, what's going on here? So you highlight, hang on, I'm measuring the change in the second derivative here. This tells me there's a change in the concavity. There's a change in the second derivative, so it's got to be a point of inflection. Again, a lot quicker than drawing up a table of values. But also, what I said before, if it's a complicated function to find the derivative of, it's probably going to be pretty difficult to find the third derivative. So the table of values is going to be a better way to go. But when you're talking about a simple polynomial or something like that, very easy to differentiate. This way of doing it is far superior, doing it that way. Okay. We'll add 4e. Oh, exercise jolly good fellow. Well, there we go.